This presentation is a follow-up to the previous presentation. In that one, we looked at how you can best approximate one vector by another. In this one, we'll examine how to approximate one signal by another. And this material is a bit abstract, and it's also a bit difficult. So you might want to review the previous lecture before if you do not completely understand it. Now, thinking about the difficulty, actually, it might be best to get out the difficultometer and try to measure exactly how hard this lecture is going to be so you've got an idea of what's ahead of you. So let's get that out right now and let's hook it up. Okay, here we go. Whoa, 7. This is going to be a hard one. Hope you're ready. So we're asking the question, how can you best approximate one signal by another? So suppose you want to approximate signal V of t by signal W of t. So V of t looks like a little sawtooth here, and W of t is a pulse. We're going to proceed exactly as we did in the lecture on vectors. We're going to first describe an error. So that's E of t is V of t minus A W of t. And we're trying to choose A so as to get A W of t to approximate V of t as well as we can. To do this, we need to measure the size of E of t. And for this, we're going to use the energy. And we'll call that epsilon. So we're following exactly the same notation as we did in the lecture on vectors. So here we've written out the energy of signal E of t. And of course, by the definition of energy, that's going to be the integral from minus infinity to infinity of E of t squared. Now, substituting for E of t, V of t minus A of W of t, we'll then plug that in, and then we want to pick A so as to minimize epsilon, the energy. This is following exactly the same idea that we did in the previous lecture on vectors. So now let's do the algebra. We'll expand out the square, and that will give us epsilon is equal to the sum of three integrals. One is the integral of V of t squared, another is the integral of V of t W of t, and the last is the integral of W t squared. And you'll notice the parameter A shows up in the second and third terms. So here's energy written out in terms of these three terms. And this is rather cumbersome from a notational point of view to have all these integrals, so I'm going to define some new notation here. I'm going to say the integral from minus infinity to infinity of signal x of t times signal of y of t is going to be x of t circle product y of t. So I'm just inventing some shorthand here so I don't have to keep writing out all these integrals. So just remember, x of t circle y of t stands for that integral from minus infinity to infinity of x of t y of t. So given that, I can now define my energy in terms of the signals. So it'll be V of t circle V of t minus 2a V of t circle W of t plus a squared W of t circle W of t. So we now have a nice, pretty way of writing out our energy in terms of our signals, and we don't have to show all those integrals. And furthermore, you'll notice if you go back to the previous lecture that this expression for epsilon looks very much like the expression for epsilon in that lecture. So here I've written that expression again, and here I've highlighted the value of A. We're trying to pick the best value of A so as to make epsilon as small as possible. And to do that, of course, just like last time, we'll take the derivative of epsilon with respect to A, set it equal to 0, and solve for A. And when we do that, we'll find A star, the best value, is going to be equal to V of t circle product W of t divided by W of t circle product W of t. And this, of course, should look very familiar. It looks just like the expression we saw in the last lecture. So let's make that comparison explicit. On the left-hand side, we have vectors, and on the right-hand side, we have signals. In both cases, we're trying to approximate V by A times W. We found for vectors the best value of A was A star equal to V dotted with W divided by W dotted with W. For signals, the best value of A was V of t circle product W of t divided by W of t circle product W of t. So you see the forms are exactly the same. Furthermore, we saw with vectors that if A star was equal to 0, that meant that V and W were orthogonal. The same is true for signals. If A star is equal to 0, that is, V of t circle product W of t is 0, that means signals V of t and W of t are orthogonal. So this gives us our definition of signal orthogonality. So let's do the example that we started the lecture off with. We have V of t, which is this sawtooth, and we want to approximate it by a pulse. Mathematically, we say V of t is equal to t if t is between 0 and 1, and it's 0 otherwise. And W of t is equal to 1 if t is between 0 and 1, and it's 0 otherwise. So we had a way of computing the best value of A, such that we multiply that A by W, it best approximates V of t in an energy sense. And we also had this definition of circle product to ease our notation. So let's do these circle products between the signals V and W, and between W and W. So when we do the circle product of V with W, we'll find out that's the integral from 0 to 1 of t dt, which is equal to 1/2. And the circle product of W and W, you can verify, is equal to 1. So substituting those values in to the expression for A star, we'll find that A star is equal to 1/2. So that means that the best approximation of V of t by A W of t is achieved by setting A equal to 1/2. So the best approximation is 1/2 W of t. So let's look at that approximation of V of t by 1/2 W of t. I think you'll agree that if we were to make the pulse taller, it wouldn't approximate V of t as well, and if we were to make it shorter, it wouldn't either. So it seems reasonable that 1/2 is actually the correct number to get the pulse to approximate the sawtooth. I want to emphasize the idea of orthogonality of signals. If x of t circle product y of t is 0, then signals x of t and y of t are said to be orthogonal. Of course, x of t circle product y of t is the integral from -infinity to infinity of x of t y of t dt. So what kind of signals are orthogonal? Some examples will help to illustrate the idea. Our example number 1 may be the easiest for you to understand. Two signals, V and W, shown on the left. V is equal to 1 for time between 0 and 1, and W is equal to 1 for time between 1 and 2. Otherwise, both signals are 0. So you see whenever V has a non-zero value, W has a 0 value. And whenever W has a non-zero value, V has a 0 value. So obviously, the integral from -infinity to infinity of V times W will be equal to 0, since V times W is equal to 0 at all times. Let's now consider example 2 on the right. We have signal V, which is equal to 1 for times between 0 and 2, and otherwise it is 0. And signal W, which is +1 between 0 and 1, and -1 between 1 and 2 seconds. When we multiply V times W, we'll find a signal which is 1 between 0 and 1 second, and -1 between 1 and 2 seconds. When we integrate that signal, the V times W signal, we'll find out that that's equal to 0, because the positive and negative areas will cancel out. Let's now look at two more examples of orthogonal signal pairs. In example number 3, we have two signals, V and W. V is a cosine wave between 0 and 2 seconds, otherwise it's 0. And W is a sine wave between 0 and 2 seconds, and otherwise 0. If you perform the integral of these two functions, you would indeed find out that they are orthogonal, but perhaps you can tell by looking at it geometrically. In example number 4, the signals V and W look a bit more unusual. I believe, though, with a little bit of thought, you can indeed verify that these are orthogonal signals. You've learned about when one signal is orthogonal to another. Let's now talk about orthonormal signal pairs. If the energy of a signal Wt is equal to 1, then Wt circle product Wt is equal to 1. This is exactly analogous to the vector condition that W dot product W equal to 1 means that W is a unit vector. Let's now define orthonormal signals. If we have two signals, W and V, and both W and V have unit energy, and V and W are orthogonal, then we say that the signal pair V and W are orthonormal. The analogy in terms of vectors for this condition are the unit vectors I, j, and k, which are all at 90 degrees to each other and all have unit length. They are an orthonormal set. So when we have a set of orthonormal signals, you can think of these signals as unit vectors, each of which are orthogonal to each other, or if you will, at 90 degrees to each other. Let's now go back to the vector case. There's some geometric aspects of this which I think we need to bring out a little more detail. So let's suppose that W is a unit vector, and let's try to find the value of A that when we multiply W by, we best approximate V, just like we did in our last lecture. And so that value of A was A star, which is V dot W over W dot W. But since W is a unit vector, W dot W is equal to 1, and so A star is just V dot W. Now we know that when we take the dot product between two vectors, and one is a unit vector, that's equal to the magnitude of vector V multiplied by the cosine of the angle between V and W. So in this case, it gives us a geometric interpretation of what A star is. A star is what we call the component of V in the direction of W. Or we can say it's how much of W there is in V. You might have heard of this referred to as projecting V onto W. So let's now look at the signal case. If W of t is a unit energy signal, then our value of A star will be equal to V of t circle product W of t. And we can think of A star then as the component of V of t in the direction of W of t, or how much of W of t there is in V of t. Let's now switch back to vectors again to talk a little bit more about components. So let's suppose that we have a set of orthonormal vectors, I, j, k, and we'll refer to this as a basis for the vector space. So we can express vector v in terms of this basis, in terms of it by giving its components. So we can say v is equal to v1 in the I direction plus v2 in the j direction plus v3 in the k direction, where v1, v2, and v3 are the components. And we can find those components by taking the dot product of vector v with the various basis vectors, I, j, and k. We can approximate signals using the same notion that we just explored with vectors. So let's suppose W1, W2, and W3 are unit energy orthonormal signals. What we're saying here is that if we have two signals, W sub I and W sub j, where I and j are either 1, 2, or 3, that W sub I circle product W sub j is equal to 0 if the indices don't match, I not equal to j, and is equal to 1 if the indices do match, I equals j. In this case, we can use this set of orthonormal signal vectors to approximate v of t in the following fashion. We'll say v of t is v1 w1 plus v2 w2 plus v3 w3, where v1, v2, and v3 are our components of the signal v in the direction of signal w1, w2, and w3. And we can find those components, v1, v2, and v3, by taking the circle product of v with w1, w2, and w3. Now I should point out that although I'm using 3 signals in terms of this discussion, there's nothing special about using 3. I could use 2 or I could use more. Any number of signals can be used to form the basis set, the orthonormal basis set, for an approximation. Let's now look at an example. And for this example, we're going to use the exact same v of t that we used previously when we were trying to do an approximation. And our w1 of t signal will be the same w signal that we used before. But now I'm going to introduce a second w signal. And this one, w2, is orthogonal to w1. And both w1 and w2 are unit energy signals, and so w1 and w2 form an orthonormal basis set. So now to find our approximation of v of t in terms of this basis set, we'll take the circle product of v of t with w1 and v of t with w2 in order to find the components of v of t in the direction of w1 and w2. And those components are in the direction of w1, 1/2, and in the direction of w2, minus 1/8. So now that we have those components, we can find our approximation. And so v of t is approximately 1/2 w1 of t minus 1/8 w2 of t. So let's now take a look at v of t and the approximation that we just found. If we graph 1/2 w1 of t minus 1/8 w2 of t, it will be the curve shown in light blue in the figure. And you see this reasonably well approximates v of t. The approximation is better than the one we found using w1 alone, which was just 1/2 w1 of t. The energy of the error between this signal and v of t will be smaller because we've used the additional component. Now the w1 and w2 that we chose in this example were completely arbitrary. We could have chosen another set of orthonormal basis vectors. Just as we may use many different sets of unit vectors for space, we may use many different sets of orthonormal signals for the approximation of signals. So let's do our example with a different set of basis vectors. We're going to use z1 and z2, shown here on this page in the bottom. And z1 and z2 are both unit energy signals, and they are orthonormal to each other. So we'll now find the components of v of t in the directions of z1 and z2 by taking the circle product. V of t circle product with z1 will be 1/2, and v of t circle product with z2 will be minus 1/4. So we find our approximation, which is 1/2 z1 minus 1/4 z2. Let's graph this approximation and see how it looks. So shown in the blue here is our approximation 1/2 z1 minus 1/4 z2, and shown in the green is our original signal v of t. And you can see this approximates it fairly well. It's better than our original approximation with just w. And w, which was the boxcar between 0 and 1 second, is the same as z1 here. We'll do this approximation example one more time, and this time we'll use a different set of orthonormal basis vectors. We'll choose x1 and x2 shown here. And these basis vectors are pulses, x1 between 0 and 1/2 a second, and x2 between 1/2 and 1 second. We'll find the components, and in the x1 direction that'll be square root of 2 over 8, and in the x2 direction it'll be 3 times square root of 2 over 8. And so then we'll have found our approximation using this set of basis signals. So now we'll graph this approximation, and that's shown in the blue line here, along with the original signal v of t. And you'll note something here, that this approximation is exactly the same as the approximation we just found using z1 and z2. And there's a reason for this. The reason is that both z1 and z2 can be perfectly approximated by a combination of x1 and x2. In our next lecture, we'll examine signal orthogonality in greater detail.